Generational evolution. It's a term I'm using to describe a theory or process for evolution that describes species adaptation through training and learned skills as taught by parent to offspring. Before I elaborate on that, one key principle needs to be addressed: animal intelligence. Though really it's intelligence across every organism, but for consistency and simplicity, I'm going to talk primarily about animals in this video. Ethology is the study of animal behavior, and is a fairly new branch of biology that is still stigmatized. As with most modern biology, ethology can trace its roots back to Charles Darwin, but not until the 1970s did a biologist named Lorenz bring ethology into the modern limelight. However, the term ethology is widely debated, and more often the field is called behavioral biology, because ethology implies emotions and behaviors closely related to human ones. Anthropomorphism is a word to denote human mannerisms found in nature, and it is intensely stigmatized in the scientific community. However, research is slowly changing that view. Animal intelligence is real, and they are not simply instinctual automatons driven by biological imperatives such as reproduction and survival. Here's why that's a wrong assumption. Many animals hunt for sport, such as cats, birds, and spiders. Primates express joy in reuniting with partners and friends, and sadness in their separation. Gorillas sing when they are happy. Elephants, furthermore, are known to cry tears in moments of sadness and fear, and orphan elephants who saw their parents killed by poachers will wake up in the middle of the night screaming and crying. Crying is seen in other animals such as dogs, and likely many other species. Yet with such a stigma on animal emotions, it's hard for biologists to say animals have reactions based on emotions without being ostracized by the community. One instance showed that a type of honeybee attended and mourned the funeral of a beekeeper who lived and was buried 7 miles from the hives she worked with. Altruism has been documented in animal-to-animal relationship and animal-to-human relationship. These are cases of one species of animal putting its life on the line for the sake of another animal without any regard to the supposed reproduction and survival instincts that turn them into biologic machines. Snakes that hunt frogs will team up with their natural prey in order to defend bird attacks. Other symbiotic relationships can be found all over nature, which suggests a level of trust and mutual understanding, if not through some form of communication. If the biological instruction dictated that all animals be selfish creatures of instinct and habit, why do these relationships keep emerging? Why do animals hug and kiss for pleasure? Why do animals play pranks or laugh at things they find humorous? Dab chicks, which are small, tailless birds, pull and peck at the tails of swans for no apparent reason. At least, there's no reason if observed under the mindset that animals lack intelligence. Sometimes animals do things for pleasure or curiosity. A herd of elephants in 1997 broke into a liquor distillery for the express purpose of getting drunk. In their belligerent rampage, they demolished the entire village. Elephants are known and feared in India for being fiends for alcohol. Birds, too, will sometimes purposefully eat fruits that have fermented in order to get drunk, and some birds can even develop alcoholism. Butterflies as well have been known to get drunk and lay around for days, unless they risk damaging their wings and flying drunk. Animals enjoy altered states of consciousness, such as drunkenness, and a large number of bird species do something called anting. They will extend their left wing over an anthill and let them sting and bite them. The birds derive pleasure from this, but there is debate over why. Again, biologists are reluctant to say that they do it for the sake of having fun. Perhaps something in the ant venom gives them a high of some sort. Birds will also do a similar process but with chimney smoke and fires, getting the same alleged pleasure. Catnip is essentially the equivalent of ecstasy or LSD for humans, but in a wild 10-minute trip for cats. Animals dream and can play out scenarios in their sleep about past events and other abstract scenes, as is the nature of dreams. They can have nightmares too. Though mostly dreaming has been found in mammals, possibly because of the presence of the pineal gland, this trait ultimately derives from reptiles, who can dream as well. In fact, one lizard species, the tuatara, has a prominent third eye. Their pineal gland is exposed by a tiny hole in their skull, though it is still under skin. However, their pineal gland has a lens and a retina that connects it to the outside world. But because it lacks an iris, the function seems to be more for reading light levels and not images. Though the pineal gland and third eye are still a controversial subject, that part of the brain in humans is called the reptile brain because of this evolutionary connection. Birds too share this common origin. Animal pharmacology has been documented in various primates. Chimpanzees rub aloe leaves on their skin to soothe wounds. Baboons chew leaves from the candelabra tree to ease pain from menstrual cramping. Tanzanian chimps eat leaves from the ziziphus and combretum plants to induce abortions. They also roll up aspilia leaves and put them in their mouths to absorb the herbal chemicals which kill harmful bacteria and also function as a stimulant like caffeine. They do this first thing in the morning to benefit from the effects. Some howler monkey females eat certain plants to determine the gender of their babies. Due to an electrical process of attracting or repelling sperm either carrying X or Y chromosomes, depending on the gender that the monkey wants to have. Birds employ aromatherapy to use insecticides to protect their nests, and one female elephant in Kenya, who was observed for a year straight, was seen traveling a long way to find a tree that had not been seen in its diet before. It devoured the whole tree and a few days later gave birth. The tree leaves and bark are used traditionally by the local women to make a tea that helps promote contractions for either labor or abortion. On that note, certain ants farm fungi that they can use to prevent infectious viruses and bacteria. There are thousands of more examples of animal behavior for purposes deriving from what can only be described as intelligent decision-making. Animals build shelters, use tools, problem solve, try new things, use drugs recreationally and medicinally, show affection and remorse, communicate, team up, abort babies, laugh, joke, prank, relax, hunt for sport, host complex communal gatherings, recognize their reflections, enjoy things for pleasure, get angry and frustrated, mourn their dead, express loss and sadness, sing and joy. They do everything we humans do, who are animals in all the same ways. Perhaps one of the biggest underlying reasons for this anti-animal bias is religion. Christians have shaped the Western belief systems, whether you like it or not, especially science during the Renaissance period and the Dark Ages. A topic for another time, but I just want to point out that the brainwashing of hierarchy our species has received. We believe humans are the top of the world, both morally and intelligently. Out of principle, biology denies anything that anthropomorphizes any organism and will seek to explain away any behavior as serving some built-in imperative survival function. Everything in the animal world, which is really the same as our own, is made out to be like a Freudian prerogative, only for survival and reproduction. Nature versus nurture has already been studied in primates. What they found is baby monkeys prefer the nurture of a fake monkey mom with a warm blanket rather than the fake monkey mom with food, though the conclusion was just that it helps with survival. But is it really so hard to believe that a baby monkey wants its mother? Another reason for the animal intelligence stigma is the unethical testing, farming, and killing of animals in the clothing, makeup, food, medicine, zoo, hunting, plenty more industries. We don't want to think about how the cows in meat farms who live knee-deep in their own waste are suffering emotional damage from living in traumatic conditions their whole lives, never even seeing the sun, and then being brutally slaughtered. PETA had it right when they compared the Holocaust to meat farming. Farmers have started putting VR sets on cows to give them screens of lush pastures and sunny plains. The results were a much less stressed out cow, and therefore a healthier cow. It is a profoundly sick practice, but I just wanted to outline some of the societal norms likely in the way of advancing our understanding of biology. Animals vary from one to another, and animals must learn from their parents or themselves or even other animals. Birds aren't born knowing how to fly and must be trained. Ants can fail in jobs and so be trained in a different field. Bats learned how to change the pitch of the frequency of their ultrasound echolocation in order to surprise insects that could hear the normal frequencies. The result is slightly less accuracy in their reading, but a better opportunity to catch prey. Similarly, mammals need to learn how to hunt and pick up on tracks and avoid predators and understand the pharmacology of different plants and insects. These are learned traits, not biological instincts that happen to natively be in all living organisms. The mere fact that we can train animals like dogs or dolphins to do tricks should be enough evidence to warrant further research on free behavioral choices of animals across the board. They have the capacity to learn and are not born into any roles, yet we still claim they are automatons. Establishing and understanding animal intelligence and sentience is only the first part of the argument. A follow-up video could easily be made on that subject alone, but for now I'm going to move on to why it's relevant for evolution. I'm going to use raptors in the Cretaceous period in an abstract example. So birds evolved from raptors. That much we can determine based on fossil record. A raptor runs with powerful legs and birds glide with wings. How did it happen? Let's say during its lifetime, one raptor needed to use its weaker, clawed arms to either reach a new food source or to move an object or remove an obstacle. Meaning at some point, a raptor learned to use its arms for a specific task that was either particular to that raptor or a common problem that arose for all raptors due to environmental changes. The asteroid that killed most life at the end of the Cretaceous period is one possibility. Either way, upon learning and discovering a new clever way to use its arms, it conditioned itself to rely on those arms more and more throughout its lifetime. The result was slightly bulkier or leaner arms. More muscle grew to adjust the newfound workload, which is basic weight training and muscle building principles. The more you use an organ or muscle, the more it develops. The less you use, the more it atrophies. This raptor successfully survived and mated. Its newborn offspring, however, share none of its newfound arm strength. Its DNA had already been deeply established. When the baby raptors are growing up, they learn from their parents to use their arms for this new purpose. Growing up with the constant use has elongated the bones of their arms and fingers, developed far more muscle and make it a more coordinated limb. These second generation raptors now have physically different arms due to their lifetime of use. This process is especially effective during periods of early growth and development, when bones and muscles are more malleable during childhood. Bigger and more stretched out arms mean more DNA, new DNA that the parent never had. Meiosis offers the possibility of passing this new arm, keeping in mind the change is still relatively minute, to the next generation. Third generations now have this new DNA code, allowing them to inherit and develop the new long and more muscular arms. They are predisposed to developing the new arms, but don't necessarily have it growing readily. Like their parents before them, they are taught to use the arms for the task. The predisposition allows for more rapid growth of the arms at earlier ages. Though, because the task is quite simple, only so much muscle grows before the arm is never challenged further. At this point of optimum gene inheritance, the point where the slightly bigger arms are now as much a part of their growth as any other trait is. The next generations of raptors will hardly need to be taught, since their arms naturally can complete the task at birth. To understand that idea, look at an object that can be grasped. You only need to see that object before knowing that you can pick it up. These muscles develop and the raptor learns a new skill, and he or she passes it to the next generation, and the generation develops it from a young age, and so on. Now we have a large family of raptors with arms too big and hulking that it affects their running. Perhaps their heaving arms gives them more momentum, and so they learn to run with arms swinging in sync with their legs. They constantly pull their fingers tighter to allow for better wind and reduce air drag. The fingers close up as they force the bones closer. Skin grows over, and now we have the early precursor to the wing. You see, the basic bone structure of bird wing is not a flat board, but it is a multi-fingered spread, just under a different outer layer. The strength gained from flapping its wing arms give it further strength. Learning the new flap run from birth meant a lifetime of that shaping of bone and muscles, until we have a raptor species that looks closer to a modern bird than a dinosaur raptor. Leg use was reduced, and wings started aiding and jumping. At some point, one daring or desperate raptor had to leap over a ravine, or jump down a steep incline, or perhaps was bored and wished to test its own athleticism, and jumped and flailed its wide arms and discovered the principle of wind resistance, slowing its fall or thrust and propelling itself slightly higher. In a more topographical terrain, the raptor trains to make bolstered leaps or assisted falls, and the next generation uses its legs even less, letting the muscle atrophy in the bone to shorten. The wings continue to get larger as each generation that makes a breakthrough in gliding must then support its own weight with its muscular arm strength. Change of diet and use causes the bones to be brittle and more hollow, reducing weight and allowing it to glide on the wind. Different relatives of these raptors give rise to the different bird species today. Why some still don't fly and some do. Whether one single family is due to credit of birds or multiple raptors of different species and locations, all venture into the creative world of invention and problem solving, and the struggle of adaptive survival and the importance of nurture and mentoring is an open possibility. This is why generational evolution makes sense. A species evolves itself through training and learning. New skills are inherited through genes after a couple generations have established a trait, and the process excels within a few generations, not over millions of years, as random mutations give rise to different traits. Background evolution, as I think it should be called, is the more traditional theory of evolution. This would be increased oxygen levels on the planet, higher or lower temperatures, and other pollutants, and general biome changes. But all that really means is an animal has access to different chemicals which cause changes. More oxygen means better quality of blood, and therefore larger bodies. That's why the dinosaur eras saw such massive creatures, because oxygen levels were far higher than they are today. Diet also plays a rapid role in evolution. New food sources means different intakes of chemicals and minerals, which then change DNA. An example in humans, though part 2 of this video deals specifically with humans, are diseases inherited from parents. Type 1 diabetes was an extremely rare disease only 100 years ago, but due to a changing diet, it is now an inheritable disease. In North America alone, there are around 40,000 new cases every year of diabetes. Around 1.5 million Americans have type 1 diabetes, and over 180,000 were children and adolescents. The trend shows that newer generations have more chances of being pre-diabetic. Clearly, the propensity for diabetes is being passed on from generation to generation within only a couple generations, not over tens of thousands or millions of years. But like I said, this is more for part 2. Back to animals. Since animals are intelligent, we need to re-examine how we think evolution occurs. The ability to learn and try new things out that is not based around mutated instincts completely changes the dynamic. A species can evolve over a few or a couple dozen generations, or it can be longer, or they don't evolve at all. Crocodiles are one of the oldest surviving species of animal that has remained largely unchanged for 200 million years. What is interesting about this is the flaw in contemporary evolution theory, because mutation and change in environments over such a long period would dictate that the species should change over that lengthy time period. However, because a species can choose to live its life however it wants to, there are families of crocodiles that never learned and trained new traits, and maybe because they didn't need to. But what we also see are relative reptile species of the crocodile, meaning that there were some families that were either forced or chose to do different things, which led to a different evolutionary path. Perhaps if crocodiles were an isolated case of this, the modern theory could still hold up. But we see mosquitoes, sharks, beetles, jellyfish, crabs, sponges, possums, platypus, and many more as all being very similar to fossil records we have of them dating back millions of years ago. If mass extinction events, fluctuating temperatures, bacteria, and viruses aren't enough to cause mutations in a species, then it begs the question if that is the primary reason for a species to evolve. Time isn't the main factor in evolution. It is learning and change in diet, oftentimes caused by trying new things or sometimes through necessity. On one hand, we see organisms remaining largely unevolved for millions of years, and on the other hand, we can observe some organisms evolving within our own lifetimes. In part 3 could easily focus on plants, but a few quick examples are some fruits which have radically changed in the last couple hundred years or less. Bananas in the 1800s were short, stocky, and filled with seeds, but were cultivated and bred by humans to be larger, seedless fruits. Watermelons followed a similar path, as being filled with more seeds than flesh. Eggplants were called eggplants because they were white and round, though now they are purple and elongated, just to name a few. But back to animals. Dogs were domesticated by humans because any dog that wasn't docile to humans were hunted. They had to learn to be pets and even evolved to have more human-like features. Again, not something that occurred over such a long period. There is debate around the first domesticated dogs, but somewhere around 12,000 to 15,000 BC, we have evidence of dog domestication, though some believe it happened somewhere between 20 to 40,000 BC. In modern times, dogs in America have evolved to be aggressive towards anyone with dark skin. Ideologically, they probably aren't racist. Rather, it was from hundreds of years of training and conditioning that eventually became an inherited gene. During colonialism in early America, dogs were trained to attack the African slaves, and still to this day, many dogs are aggressive toward black people. Cats learn to meow in high frequencies to mimic human children crying or whining in order to be pampered by humans. Animals living in ecosystems far removed from humans have not learned to be wary of a human, meaning someone can approach something like a bird or a squirrel without it being afraid in places where humans haven't systematically hunted them. Inversely, cities have animals that are okay with close human contact because little to no hunting occurs in cities. Prey and predator relationships are learned and therefore can be inherited, as with the case of dogs in America, but aren't automatically hardwired into their brains for no reason. One animal will react differently to a situation than another animal in the same family even. It comes down to their experience and personalities. This video is already pretty long, and a few follow-up parts will need to be made. I wanted to go into microscopic subconscious intelligence as well, but that will need its own part. Part 2 will be human intelligence and evolution, and part 3 either plant or insect and microintelligence. Obviously, animal intelligence and evolution are highly debated and sometimes controversial topics, so if there's any discussion in the comments, please be respectful and polite and keep an open mind. But I encourage people to express their thoughts and ideas, observations, questions, rebuttals, and criticisms. There's a lot to cover on this subject, so if there are points you want me to expand on, please let me know. I'll either respond there in the comments or add it in a future part. But yeah, I think that does it for part 1.